Salutations, mini mathematicians! Welcome back. 3.2D, modeling backwards distribution. Here's your lesson purpose. We're going to use an array model to show the factors of an expression that was distributed. We're going to fully factor the expression using the GCF, otherwise known as the greatest common factor. To fully factor and simplify, we have to use the GCF. So 30x plus 6, we could factor it as 6 groups of 5x plus 1 or 2 groups of 15x plus 3, but this is not fully factored because notice 3 still will go into 15 and 3, so 6 is the greatest common factor of 30 and of 6, so that's why we want to use the greatest common factor so we can fully factor. Let's get going. You may be asking yourself, what is an array model? So a little reminder, if you ever need to pause the video at any time to write down what I'm writing down, please do so. You're going to do great. What is an array model? Well, just array itself is a point with a line. So an array model is two rays together meeting at a point. And we use them to show products before. So if we were doing 1 times 3, we'd say 1 times 3. So the factors are 1 and 3. And what goes in the middle is kind of the area. So you also use them for area models in the past. So this product or area is 3. Here, if we wanted to do a 2 by 3, notice we put 2 blocks on the outside here and 3 on the top because the first factor and this is the second factor. And then if we look at what is in the middle, we would just extend out 3 2 times or 2 groups of 3. And we could color it in. So our factors here, the numbers that are multiplying to make the numbers, are 2 and 3, and our product or area here is 6. Very nice. Let's keep looking. A little reminder, a single one, we like to use a circle, an x squared, or an x, but in this case we are going to use a little square for our singles to make the modeling easier. So when we have a 4 by 4, we have 4 being multiplied, so we're going to make 1, 2, 3, 4 little squares on the outside times 4 with 1, 2, 3, 4. So on the inside, remember the first factor is the number of groups, so we're going to have 1, 2, 3, 4 groups of 1, 2, 3, 4. So you would have 16 in the middle. So our factors are 4 and 4, and our product or our area is 16. Very, very nice. Looking at our next one, x times x. Remember, an x is just a rectangle. So we have one rectangle and another rectangle, and if we extend those out, remember that is x squared. Very, very nice. So our factors are x, and our product or area is x squared. So looking at our two models above, why do you think 4 squared is called 4 squared and x squared is called x squared? Well, that's because 4 squared is 4 times 4 represents the dimensions of a square since they have equal sides. Represents, when I say dimensions, I mean side lengths. Side lengths or dimensions of a square with side length 4 and area 16. Very similarly, x squared, which is equal to x times x, x is 1 side length of a square. X squared is the area. Nice. let's keep expanding our knowledge of arrays to our algebra tiles. So it says to build the factors of 3 groups of x plus 2 on your desk and then build the rectangular area model. We're not going to build those factors and then make the rectangle in the middle. We are just going to look at this is the first factor and then this is the second factor and look at what our area is. So the factors of our multiplication problem are 3 and x plus 2. So the dimensions of our rectangle are 3 by x plus 2. So our area is going to be in the middle. So we're going to have 3 singles, 1, 2, 3. I'll put 1s in them. And then we're going to have an x and 2 singles on top. Notice when we draw in what's in the middle, we just extend out our lines that we have on the outside of our factors. So here we have another x, 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 and these are all singles. So our area here, if we count in the middle, is 3x plus 6. So the product of our multiplication problem is 3x plus 6. Nice. Let's look at the next one. So we have 3 groups of 2x plus 1. So we're starting with 3 on the outside. Again, we're going to draw the 1s in there so we can clearly see that those are singles and not really short x's. And we have 2 x's, x and x, and a single. So again, remember, distribution is just fancy multiplication. So here we have 3 groups of 2x and 1. So here's one group of 2x and 1. Here's a second group of 2x and 1, and a third group of 2x and 1. And we're going to draw in our x's, and we're going to draw in our 1s. So the factors of the multiplication problem are what are on the outside that we multiplied together. So we have 3 and 2x plus 1. So the dimensions of our rectangle are 3 and 2x plus 1. The area is what's on the inside, right? These are our side lengths, so what's on the inside is 6x. Oh, I should use the other color. 6x plus 3. See, now they match. 6x plus 3. Perfect. So we're going to do one more together, and then you're going to finish the page on your own. So now our factors are 2 and x plus 4. So we're going to have 2, 1, 1, and then an x and 4 singles, 1, 2, 3, 4. And maybe you already know this is going to be 2x plus 8. That's great. We want to be able to show that with a model so we can understand distribution better. So again, what are our factors, also known as our dimensions? 2 and x plus 4. And what is our area or product here? That's what's on the inside, is 2x plus 8. Perfect. Why don't you finish the next 2 problems on this page, and we'll go over them in just a moment. You pause the video and finish. Perfect. Let's take a look at how we did. So the next problem, we had our factors of x and x plus 3. So here's x plus 3. And then on the inside, x times x gets you x squared, and then x, and x. So x squared plus 3x. Notice the x squared terms comes first. When you have variables with an exponent, they have a higher power, and the larger the power, the more priority they have when you're writing our expression. And the last one, your model should look like this, x, and then x, and 1, 1, 1, 1, 1. Please make sure you are labeling your tiles for array models. Very important. Our factors or our dimensions are x and 5x plus 2, x and 2x plus 5. And then our area or our product is 2x squared plus 5x because you have 2x squares. Nice. Let's keep going. Next, what we're asked to do is to explore simplifying the expressions below in using a model and words to explain the difference between the two expressions. So we've been working with these a lot. When you have x plus x, the model might look like this, which simplifies to be 2x. Here you are adding like terms. Two x's to equal 2x. However, over here, we can't just have a chip or tile model or an algebra tile model. We need an array to show that x times x gets you x squared. So here we are multiplying 2 x's to get an area, you think of it as an area, of x squared. So very important, x plus x is 2x and x times x is x squared. It's something you're probably going to be going over multiple times throughout your mathematical career. So let's take a look at the next one. 9 is model the expression 2x plus 4 on your desk and then build the pieces into a solid rectangle. So that's what's making that area model, and then find the factors and write 2x plus 4 in factored form. So first thing we're thinking about is our dimensions. So our dimensions, we're kind of going backwards here. We're going backwards. So if you had 2x and 4, we want to think about our GCF. So now that you're so good at multiplying two expressions together, our GCF here of 2x and 4, you guessed it, is 2. So 2 is what's going to be our number on the outside. And if we write this, it's going to be a rectangle. So 2 groups of what is going to get me 2 x's? That's right, 2 groups of x is going to get me 2 x's on the inside. 2 groups of what is going to get me 4 on the inside? That's right, 2 groups of 2. So the dimensions or factors of our rectangle are 2 and x plus 2. So the area with our model is 2x plus 4. So remember, if they give us an expression like this, this is the area, and they're looking for the dimensions. Area as a sum is equal to the area of a product. Area as a sum is 2x plus 4. Notice that is just the sum. Area as a product is 2 groups of x plus 2. Notice we're writing this as a product. Yes, there's still addition in it, but we are multiplying these two together. So the right side of this equation represents the factored form, so that's right here, where we have taken the greatest common factor, or GCF, out and left us with x plus 2. Nice. Now that we looked at that a little bit, let's continue to do a few more examples. The directions are model the expression by dividing the solid rectangle, find the factors and write in factored form, reverse distribution form. And I always want to be thinking about what our GCF is, and we wrote it right down here. So our GCF of 6x and 3 of all the terms is 3. So we know we're going to have 3 singles over here. And then 3 times what gets you 6x? 3 times 2x. So we're going to have 2 x's up here. And then 3 times what is going to get me 3? That's right, that's 1. So we're going to have 1 here. Oh, sorry, this is 2x plus 1 and 3. Those are our two factors. And if we look at what's in the middle, or our area, 1, 1, 1, x, 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 we have 6x plus 3. So in factored form, it's 3 groups of 2x plus 1. Nice. Let's look at 11. So when I'm looking at 11, I have 3x plus 12. So our greatest common factor of 3x and 12 is 3. So we know our factors are going to be 3 and what? Well, if I draw out my 3 here, 1, 2, 3. 3 times what is going to get me 3x? Oh, 3 times x. 3 times what is going to get me 12? 3 times 4. So our factors are 3 and x plus 4, so in factored form is 3 times x plus 4. And when we finish our array model, we see, sorry, my lines could be so much better today. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, and 3 x's. Yay! Let's do one more together. So we're going to do number 13 together. So again, we have our area as a sum. We want to think about the GCF. The greatest common factor of 6x and 2 is 2. So we know we're going to have 2 singles over here, and our factor is going to be 2 and something else. 2 times what gets me 6x? 2 times, that's right, 3x. 2 times 3x gets me 6x. 2 times what gets me 2? That's right, 1. So our factors are 2 and 3x plus 1. And we extend out our lines. We see in the middle we have our 6 x's and 2 singles, making reverse distributed form or factored form 2 groups of 3x plus 1. Yay! Okay, pause the video, finish this page, and we'll go over it in just a moment. Let's see how y'all did. Number 12. Number 12, we had 5x plus 10 is the area on the inside. So what are the factors or the dimensions of my rectangle? The greatest common factor is 5. So this should say and. So 5 singles, 5 times what gets me 5x? 5 times x. 5 times what gets me 10? 5 times 2. So I have 5 singles and x plus 2. 5 groups of x plus 2 is going to get me our factored form. Taking a look at 14, the GCF of x and 4 is 1, so the factors are 1 and x plus 4. In reverse distributed form, it's one group of x plus 4. I know, we've talked about not writing the 1, but in this case, we want to see what the products are, so we want to see both of those expressions. It's one group of x plus 4. And that's what your model looks like. Over here, the GCFs of x squared and 3x, that one was a little bit tougher, but that's x. So x times what gets you x squared? X times x gets us x squared. We've looked at that quite a few times this module. And then x times what is going to get me 3x. X times 3 gets me 3x's. So in reverse distributed form is x groups of x plus 3. Wonderful. Let's look at our last page. Looking at our last page, we are going to do 16 and 20 together, and then I'll let you finish the other ones on your own. So remember, we're writing in reverse distributed form, factored form, and use a model if you'd like, but I think you guys have it right now. So our GCS of 30x and 6 is 6. 6 times what gets me 30x? 6 times 5x. Plus 6 times what gets me 6? 6 times 1. And you can always double check. It always is worth it being like, okay, 6 times 5x gets me 30x, 6 times 1 gets me 6. Always double check. Here's a double check for you. It's such an easy thing. You're so good at distributing. I don't want you to mix that up on the exam. Okay, 4b plus 28, my greatest common factor is 4. Oh, I told you we were going to do 20, but we'll do this one too. Why not? And then 4 times what gets me 4b, 4 times b, plus 4 times what gets me 28, 4 times 7. Take that moment to double check. 4 times b gets you 4b. 4 times 7 gets you 28. That's your double check. Okay, 20. The greatest common factor of 25b and 5 is 5. 5 times what gets me 25b? 5 times 5b minus, I know what, we haven't had one of these yet. 5 times some negative number gets me negative 5, negative 1. So this is new, we haven't seen it this lesson. Always double check. 5 times 5b gets me 25b. 5 times negative 1 gets me negative 5, and I'm double checking that that's right. So I want you to finish this page. So you're finishing 18, 19, 21, and 24, A and B. Pause the video now, and we'll go over it in a second. Let's take a look. 18, 3 groups of m minus 5. 19, 2 groups of 2n minus 1. 21, 4 groups of x minus 2. So how else might 16, 17, and 21 be factored? You could factor them some different ways. So 16, we could think of 2 groups of 15x plus 3, which is the same as 3 groups of 10x plus 2, but they're not going to be completely simplified because we didn't use the GCF. So we have to remember we have to use the GCF. So how do you know if an answer is fully factored? You know an answer is fully factored if you're using the greatest common factor to represent the number of groups. The first number, you're multiplying the first factor. Inside the parentheses, there are no common factors left over, making the expression fully factored. So inside the parentheses, the greatest common factor is going to be 1. It's kind of like when you simplify fractions all the way. If you had something like 24 over 6 and just divided by 2 first, you'd have 12 over 3, which you might think is fully simplified, but the greatest common factor is not 1 yet, so you'd have to do 3 again, and that's how you get 4. So make sure, if I had simplified from the very beginning using my greatest common factor, I would have gotten my fully reduced answer. So same, you've been doing this for a while. Great job, mini mathematicians. Excellent work. Video bar out.